So, we're going to talk about end-to-end encryption today in 2017, what you need to do it. This talk, just forewarning, is not going to give you everything that you need to know to do end-to-end encryption. This is by far one of the most difficult things that I've ever personally studied, and it's going to make your head hurt. So just embrace that. You won't understand everything on the first pass. My hope for you is that I can essentially impart to all of you the lessons that I have learned over the past 8 months of trying to implement my own secure messaging app. By the way, there's not a demo of my secure messaging app because I'm still figuring out how to do all the end-to-end encryption for the protocol for that to work. So we'll talk a little bit about all the component pieces, and hopefully you'll leave this talk with a good understanding of the foundational pieces that you need in order to build out your own protocol. So here's the current state of things, right? Like why should we care about end-to-end encryption in 2017? Well, the first thing is governments want our data, right? Britain wants our data. The US government wants our data. Everybody wants our data. Germany wants our data, right? Germany and Russia and China and everybody, we're all taking each other's data. Bruce Schneier actually has a book on, I think it's called, does anybody know what it is? It's the one he just put out. Data and Goliath, I think is what it's called. It talks about all the different things that we're doing to snoop on each other's privacy. And that's essentially the world that we live in, right? We live in a world where Julian Assange gives people private information on corporations, but he doesn't get consent, so he goes to jail. And Zuckerberg gives corporations people's personal information, but he's man of the year, right? Because he got consent, right? And you're thinking, but I just want to send photos and messages and videos to family and friends and keep my privacy. Like, can I do that? Nope. You cannot. That method is not allowed because you accepted the EULA. And then you think, well, how about my identity? Can I keep that? Is it possible for me to protect that? Nope. You can't do that either because Equifax just blasted all your junk all over the internet. So good luck. Right. Lock down your accounts. I highly recommend putting a credit freeze on all of your stuff. So by the way, this is a normal response to seeing the reality that Equifax executives took 40 days to inform the public, but it took them 3 days to sell 1.8 million in stock when they realized that they'd messed up. So it made me want to eat my pets. So what can we do, right? What are we to do? This is a crazy, strange, frightening new world, right? We're going to npm install, right?
Yes.
Or at least that's what I thought. Right? Yeah. So I thought, I'm going to npm install. I'm going to solve this problem. We're going to figure this out. Turned out to be a lot harder than I initially thought was going to be. So a partial solution to this crazy new world that we live in is you want to encrypt your data before it ever hits the network, and you want to communicate using secure systems. If you encrypt your stuff before it ever goes over the wire, then there's nothing that a server can do to it, but the person that you're sending it to, they can take it, and provided that they've got the right keys, which is actually a big problem. Ensuring that they have the right keys is a big problem. As long as they've got the right keys, they can read it and nobody else can. This is the beauty of asymmetric encryption. So here's where we're headed in our JavaScript encryption adventure today. The first thing is we're going to look at minimum standards for secure encryption, specifically for communications in 2017. We're going to talk about 3 essentials for secure communications. We're going to talk about symmetric encryption algorithms and ciphers. We're going to talk about asymmetric encryption, and we're also going to talk about authentication and man-in-the-middle attacks. We're not going to go super in-depth on man-in-the-middle attacks because there are already some great resources out there that kind of give a general overview of that. But we're going to explain technically why those things happen. We're also going to look at currently available JavaScript libraries that you can use for encryption and authentication. There aren't a whole lot of them. And then we're going to take a very shallow dive into Signal Protocol, why it was developed, and a little bit about how it works. It goes over my head. It's probably going to go over your head too. That's okay. We're all in this together. We're going to figure this out, right? We're going to do this. Partially because I think we kind of have to if we're going to continue to be just sane human beings. So here are minimum standards for secure encryption in 2017. What we're talking about when we talk about a secure messaging protocol is we're talking about creating a system in which 2 or more people can communicate with each other securely. When you combine encryption, authentication, and message numbering together, you end up with a protocol, specifically a secure messaging protocol. Protocols are really, really hard to implement well, and they're really, really hard to test. Right? Security experts who've been doing this for 20 years have had issues with creating protocols where then they go back 5 months later and they realize there's a hole in it and they've got to patch it. So it's very difficult to do this. Guess what I inadvertently set out to do when I was going to build my cool little secure messaging app out of my walk-in closet? Right? I set out to make a protocol. So far I had failed. Right? Hopefully you will not. Right? But that's okay. There's freedom to failure. Right? So here are the 3 different pieces, and this is why that these 3 essentials are needed for a secure messaging protocol. Encryption prevents attackers from reading your data in plain text. Right? This actually encapsulates your data and prevents people from reading. Authentication prevents attackers from swapping out your data for their data, or from even like changing a few things in it before it gets to the recipient. This is part of what deals with man-in-the-middle attacks. There's a person that can sit in between you and the person that you're trying to communicate with. And if you think about it, if there's no authentication, we'll do it this way. Can I get like a couple of volunteers? So like if Thomas is here, and if Eric is next to him, and let's say that I'm the man in the middle. I don't know if you're going to see me on camera here, but
yeah, everybody scoot this way.
Yeah, okay.
Yeah.
So, are we on there?
Thomas.
Except Thomas.
Yeah, okay.
A little more.
So, if I'm in the middle, let's say that Eric says to Thomas, like, he wants to send him Cryptography Engineering. This is an excellent book. If you're interested in cryptography, you should get this. This was extremely helpful. He wants to send Thomas this. Well, I say, all right, I'm going to keep that. I'm going to send Thomas my phone.
All right, good swap.
Right? And then Thomas sends something. Thomas tries to send the phone back, but then instead of handing Eric the phone, I'm going to keep the phone. I'm going to send Eric a block. Right? I can do this all day. Right? Eric has no idea that he's not communicating with Thomas. He's actually communicating with me. The only thing that fixes that is authentication. Right? Because if Eric takes his private key, and if he signs the thing he's sending with his private key, then Thomas can get it and he can verify whether or not it was actually produced by Eric. Okay? This is just a very basic level. That's why you have to have encryption. So, okay, thanks guys. And why you have to have authentication. So, the third thing that you need to have is message numbering, because this prevents attackers from doing what's called a replay attack. If I collect all the messages that Eric sends to Thomas, then I can remix them, shuffle them up, and send them back in whatever order if there's no message numbering. They're genuine messages. They might be like well authenticated, but I can really mess with Thomas's head by mixing up all the things that Eric has sent. I can hang on to them. I can delete them and never send them. So I can just send him parts of messages. That becomes a big problem. So you've got to include message numbering to prevent that. We're not going to get into message numbering much here today, but it is part of how you should be thinking as you think about what am I sending over the wire and how am I communicating with my intended recipient. So, 2 types of encryption. There's symmetric encryption and asymmetric encryption. With symmetric encryption, you encrypt and decrypt with the same secret key, and it's fast. It requires the use of something called a block cipher that encrypts your data in chunks. It takes all of your data and it breaks it down into 128-bit blocks. The best currently used block ciphers support up to 256-bit secret keys, which are used to actually run the encryption algorithms. The problem is, though, that due to things like birthday attacks, which the birthday problem is something where if you put X number of people in a room, the likelihood that two of them share a birthday is over 53%. I think it's something like 20 people. That's your probability. You wouldn't think that it's that high, but when we start talking about doing things like hashing messages and some other things like that, you can get what are called collisions. When you get a collision, that's where a hash or a MAC of one of the things that you have hashed or MAC'd matches this. It's the same as another thing that's hashed or MAC'd, right? They should be different, but they're not. When you get a collision, it results in some really problematic scenarios. I'm not going to go super deep into that because I think for half of you that just lost you. But collisions are bad, right? The result of this is if our block ciphers use 128-bit blocks, and because of birthday attacks, we really need twice as much like encryption stuff in the tools that we're using to get a true half that in terms of our security that we desire. Like if I want 128-bit security, true 128-bit security, I really need to use 256-bit everything. Like keys, block ciphers, all that, right? So the problem with this, and where we currently stand, is that all of our block ciphers use 128 bits. Like we're only really, from what I can tell, we're only really getting 64-bit encryption. Right? Now apparently it's good enough that, I saw a news article last night, apparently the Department of Justice is now asking Apple to weaken its encryption again so that it can like get through it. So I think we're still okay for now, right? But as of 2010, something that's mentioned in here is that AES 256-bit encryption has been proven to be insecure. That was 7 years ago, right? This is the industry standard. This is advanced encryption standard. It's what's used by everyone. U.S. government uses it, everybody. So you can panic now. Right? Like, things are crazy in the world of cryptography. And so, again, don't try to retain all this at once. Just try to follow along the best you can, and hopefully, as you go back over this, you'll be able to pick this up. So, with symmetric encryption, again, we encrypt and decrypt with the same secret key. So, a block cipher is going to encrypt one chunk of data, 128 bits. If you want to encrypt more than that, you have to use a block cipher mode. Right? It essentially takes your data, chunks it into all these blocks, and then it runs, and we're going to see a diagram of this in a second, it runs the algorithms through that to mix it all up, right? There's a very specific way to do that. Some of it involves exclusive OR, which is a mathematical function that you run on things. Part of this also is that you have to use a randomized and unique initialization vector for the first block. What would happen if you used the same symmetric key to encrypt multiple things? Well, you would start to see patterns in the first blocks of the messages unless you mixed them up, right? We'll see an example of what happens if you do that in just a little bit. So this is an example of symmetric encryption. This is cipher block chaining, cipher block mode, or block cipher mode. You got your plain text. You take an initialization vector and you throw it in, and there's an XOR function that happens here. The block cipher encryption happens, and your key is injected here, and then you get a ciphertext. Right? So this is your encrypted stuff that you're going to want to send. Since we're doing a block cipher mode, though, we're doing multiple 128-bit blocks of data. Part of what cipher block chaining does is it takes your block cipher encryption ciphertext and it injects that into what's happening with the XOR, I believe is how I'm supposed to read this. Injects it into this plain text coming in through here. So the ciphertext here is mixed with the plain text of this block. That all gets run through. And you get another ciphertext for this chunk, and then you take this ciphertext and you put it in this plain text. And are you confused yet? So it mixes it all up really well, right? To decrypt, it's essentially the reverse. Right? So you've got your ciphertext, you inject a key, which this is your shared symmetric key. The block cipher decryption runs, you take the initialization vector, you XOR it, and then you get plain text. So that happens through your whole set of blocks. Once you have that, you have your decrypted message. Okay. This is why this makes my head hurt. Right? This is really hard. Right? This uses math that I didn't know existed. So anyway, here's an example of what this looks like in code. Right? I really hope that for some of you this is like super helpful to you. It took me a long time to figure this out. It took many nights banging my head on my desk, like, why won't it give me the decrypted text? Right? So here we've got our key. We set up a 256-bit key using some forged utilities. This is using a library called Forged that you can get on GitHub. We create a 256-bit IV. We create a cipher block chaining block cipher mode form of AES. Right? And since we're using a 256-bit key, we're using AES 256 as our block cipher. Okay? So the nomenclature becomes problematic, right? So then we create our cipher using our key. We start the cipher with our initialization vector. We throw our message into the cipher and we let it run. We process it and finish it here with cipher.finish. And then we get our ciphertext in bytes, right? Not as a string, not as, like, I guess you could do it as a hex value, but here we're going to get it in bytes. Now, then we send that over the wire along with the initialization vector and the symmetric key. You've got to send both your encrypted payload and you've got to send your initialization vector and symmetric key, or otherwise, if I send something to Sarah, she can't decrypt it, right? The way that we send that initialization vector and symmetric key over the wire is we use asymmetric encryption. And that's what Brett was talking about at first. So we'll get to that in just a second. Let's say that Sarah has all the stuff that she needs. So she'll take it, she'll create the decipher using the key, she runs it, and then it outputs, and you can output it to string, and you get a super secret message from Bob. Right? So, in summary, with symmetric encryption, you want to use AES with a 256-bit key and cipher block chaining block cipher mode. You can potentially use something called, I think it's pronounced Galois counter method mode. That is a different type of block cipher. It actually handles both encryption and authentication. So it's a little bit, like if you want to compartmentalize things out and not go crazy at first, you might want to stick with cipher block chaining. Cipher block chaining stands up to a lot of abuse. So if you're concerned that you may not be implementing it right, fall back to this. This is always a good standard right now. If you want to be even more secure than using AES, you can try another block cipher, which is called Serpent, but good luck finding a JavaScript library for it. I have not seen one. There were several candidates for the contest that the US government put on for who would get the advanced encryption standard label, as like this is going to be the advanced encryption standard. Serpent was one of them. The only reason it didn't win is because it's slow. But according to what's in here, in cryptography engineering, Serpent is probably the most robust of all of the block ciphers. So, but good luck finding it in JavaScript. For symmetric encryption, you never want to use a thing called electronic codebook. Here's what happens with electronic codebook. Instead of mixing things up in all of your blocks, every block is encrypted the same way using your symmetric key, right? Well, what does that allow you to do? That allows you to see the shadow pinging, right? Shadow pinging's bad. You don't want shadow pinging, right? If you try to encrypt stuff and you don't mix things in using initialization vectors and also doing things like taking the ciphertext of the previous block and XORing it into the plain text of the next block, you end up with this. This is what you get with cipher blockchain. This is what you want. This is pseudo-random data. Right? So now let's talk about asymmetric encryption. With asymmetric encryption, you encrypt and decrypt with different keys. One is a private key that you never, ever send over the wire. The other is a public key that you do send over the wire and that others can encrypt things with to send them back to you. There are two well-known systems for this. The first is Diffie-Hellman protocol, which, by the way, it was published in 1976. And RSA, which was published in 1978.
Good years.
Yeah, it was patented in 1977. We got that right. Patented before they published, I guess. So, we're still living in the 1970s with cryptography. Why? That's because cryptography is hard. So that's why I would normally not recommend like print materials and things, but you can go to print materials for cryptography. That's okay to do. Things are not developing as fast as things like front-end frameworks like Angular and React, right? You can actually get a lot of good stuff out of the academic mathematical things that are in cryptography books.
Can I ask a question?
Yeah.
Isn't that a good thing that they're old?
It is a good thing that they're old because if they are still being used and they haven't been cracked yet, then it means they're safe, right? Now there's some caveats with that because we found some weaknesses in virtually everything that we use. But we know how to limit that damage. So it's worse to use something really new and cool and shiny and that can do all sorts of cool stuff because if something breaks in there, things catch on fire. Right? We want to use the old tools that have had everything thrown at them and they're still standing. So that's part of why Diffie-Hellman and also RSA continue to be used. They're actually, like, you should use them, they're good. Diffie-Hellman works based on something called modular arithmetic, which is kind of like, it's clock math. We'll see an example of this in a second. It's a little confusing the first time you see it. So this is an example from Wikipedia. This was actually a pretty good example, so thanks Wikipedia. With the protocol, we're going to have Alice and Bob. We're going to choose a modulus, which is P. Now, ideally, P would be like really, really, really long. This is like a really, really, really long prime number. Okay? You don't want to compute that yourself. You want to have like prime number generator that creates P for you, but you're also going to have some kind of base. Alice chooses a secret. Right? So Alice chooses A, and she sends Bob G to the A mod P. Right? So modular math happens here, and you get 4. So how does this work? Well, A equals 5 to the 4th mod 23. Who knows what 5 to the 4th is?
625?
625. How many times? Well, this is essentially, to really boil it down, a remainder. When 23 goes into that, 4 is what's left over. Right? Imagine that you are doing this with, let's see, yeah, we're doing mod P. Imagine that you're doing this with like a really big prime number. It gets real heady real fast. This is kind of dirty to look at, but this is what's happening under the hood. So Alice chooses a secret integer, sends Bob A to the GA mod P. So A equals GA mod P. So he's sending 4 in this case. Or Alice is sending that. Bob chooses a secret integer 3. And then sends Alice B equals G to the B mod P. So Bob sends Alice 10. See how this is already getting confusing? So you go in circles sometimes as you read this. And you wonder why your code doesn't work and you realize that you forgot to include some key step just because you got lost in the weeds. Alice computes X. This is the shared secret. Okay? So what's happening here is Alice is sending part of what they need to make a common session key. Bob is sending part of what's needed to make a common session key, and then they get S. S can now be used, this 18, this can be used to encrypt stuff and send it over the wire.
It didn't exist before they started talking.
Yeah.
The point of the
Yeah.
asymmetric.
Right.
Is that it didn't exist
Right.
before they started talking.
They have to talk with each other. There has to be, like Alice has to send Bob something, Bob has to send Alice something to actually get the key to do encryption. This is partly why you cannot do Diffie-Hellman with someone who is not online. So if you're going to start a Diffie-Hellman message protocol with someone who's not online, you have to store what are called pre-keys on a server that you can pull down. So if Bob isn't online, but he's got 100 pre-keys stored on the server, Alice can run through those pre-keys and send messages to Bob. Bob can still decrypt them when he comes online. To expand upon this is an example of a ratchet. So K is the secret key. Alice has just received Bob's B. Right? He picks a new secret C, and then he calculates a new key, which is B to the C mod P. Alice sends Bob C, and the encrypted message E with new K. Right? So you've encrypted that message with the new K, because Alice has generated this new symmetric key here using C. When Bob gets C, and he gets the encrypted message, he decrypts the encrypted message by calculating new K equals C to his secret B mod P. Bob picks a new secret D, and then he calculates new K. Again, you're not confused yet. I don't know, it's superhuman or something. So, calculates new K. He encrypts the message using new K. And then Bob sends Alice G to the D mod P, giving her D, along with the encrypted message with new K. Alice gets D and E to new K, and she decrypts E to new K by calculating new K is D to her secret, where's it at? C, mod P. And you rinse and repeat. Right? You will go crazy if you try to implement this in like vanilla JavaScript, right? This is why we need good tools to do this. If you're interested in cryptography, please contribute to the community. We need to have good tools to do things like this. But the sum of all this is that you can use this to create a self-healing ratchet where if K is ever compromised, it only compromises one message instead of all the messages that you've ever sent. Okay? Which is why I'm going into such detail with this. I want you to actually see technically what's happening so that you can understand the severity of this. With the right tools, the ratchet can heal itself so that you only compromise one or two messages instead of compromising every message that you ever sent. If Brent sends me, 150 messages over 5 years, and we're always using the same asymmetric keys. So I've got my private key, which like if I've got a PGP key and I'm using email, everything that Brent sends to me, if the government ever knocks on my door and takes my private key, they can read every single message that Brent has ever sent to me. Every one. It is a catastrophic, with a capital C, failure, right? Diffie-Hellman allows us to create what are called ephemeral keys that don't do as much damage. You're going to compromise a message or two, but you're not going to compromise everything, right? So, Signal does this, and Signal we're going to get to later. But again, protocols are really complicated. So,
if you got a key though, could you work it backwards to get all the previous messages? Like if you had all the other messages, you got one person's key, then you have like all the previous payloads essentially of everything. You could like unratchet from before. Is that possible?
So it depends on how you set things up.
Okay.
And honestly, part of the difficulty that I have in talking about Diffie-Hellman is that there is currently no JavaScript library that I found that does it. So I haven't actually been able to throw this in and experiment with it and see what happens.
There are other programming languages.
Yeah.
Say it.
Right. We're going to get to why JavaScript is important for this, right? You can't ignore JavaScript.
That's a good question, isn't it? There's a reason why they call it forward secrecy,
Right.
right?
And
It only protects you for future messages,
right.
not for backwards messages.
Right. And we will look at both forward secrecy and future secrecy when we talk about Signal. But here's the problem with Diffie-Hellman. There is no authentication. Remember how I said that somebody can stand in the middle and they can exchange whatever they want to with people, and the sender and the recipient don't realize that they're not communicating with each other? Well, if you do not do things like sign messages with your private key, where then they can check with your public key to be sure that you sent it, somebody can stand in the middle and they can just swap out Diffie-Hellman keys as you send them, right? You get like zero verified trust that you're communicating with the right person unless you use some type of authentication. The great video that explains this is it's by Martin Kleppman and Diana Vasilik, I think is how you say it. They have a great video on this, do a lot of in-depth stuff with Man in the Middle, so I will refer you to them. It's on YouTube. A partial solution to this Man in the Middle problem with Diffie-Hellman is something called Sigma protocol. Right? There's that word again, protocol. There are going to be a lot of moving parts with that to do that. And I point you to them for more of a live example of that. I have a slide somewhere in here on Sigma protocol that will show you what happens when you sign it back. So you can also use RSA for asymmetric encryption. RSA also works on modular arithmetic and using large prime numbers. But due to its design, long messages cannot be, this should say it prevents, but due to its design, you can't encrypt long messages with it. Because of that, we usually will encrypt the symmetric key along with, if you're using an initialization vector or something like that, we'll encrypt the initialization vector and the key using RSA. And you'll attach all that to your message and then send it over the wire. So you decrypt half of it using RSA and asymmetric encryption. Then you use symmetric encryption to decrypt your really long message, because symmetric encryption doesn't really have a limit in terms of what you can encrypt. So here's an example of asymmetric encryption using RSA with AES. Bob and Alice exchange public keys. Alice encrypts her message using AES 256 to get E. Alice concatenates the key for AES and the initialization vector and encrypts that using Bob's public key. Alice concatenates the encrypted key in IV, and she does that with E, which is her symmetrically encrypted message, sends it all over to Bob. Bob gets the encrypted packet, parses it. He then parses the key in IV, decrypts them using his private key, because he's the only one who can decrypt that. Right? Alice has sent him something that he is the only person in the world who can actually unwrap that and get the key in IV to run the symmetric decryption. He parses the key in IV and he uses them to decrypt E, and then Bob reads Alice's message. So, any questions on that? Does that make sense?
And isn't this why a variation on this is what we consider building in our browsers?
Right.
Because the asymmetric encryption is quite expensive. So you will start with asymmetric encryption and then transmit a symmetric key and then use that for the rest of the session.
Right. So, and that's SSL and TLS. They keep, I think Microsoft was the one that forced people to start using another name for it or something, but they go back and forth with TLS and SSL. That uses asymmetric cryptography. So every transaction you've ever done with your bank online uses this. If you're not paranoid yet, I encourage you. So get paranoid. So summary of asymmetric encryption. Don't try to use 128-bit or 256-bit keys for asymmetric encryptions. The public keys are way long. Okay, this is part of why it's so slow. You're using huge, huge, huge prime numbers to generate these outputs. You want to be sure that you use good primes and good prime number generators when you're doing RSA or Diffie-Hellman. The encryption is very slow, and also remember that asymmetric encryption does not include authentication. Right? Do you see how many foundational building blocks we have to establish a secure protocol? Like, it starts getting so crazy. Just part of why, like, I hope that you're able to sort of see how to start walking through some of this if you try to endeavor this on your own. So now we've covered encryption. Building block 1. All right. So now we're at authentication. We want to ensure that an attacker has not tampered with our data, and we want to ensure that it came from the right person. There are a couple of things that we can do to do this. There's hash functions and message authentication codes. You also use signatures and verifying signatures, but I'm not going to go into that. The math for that is also complicated. I point you to the resources like Cryptography Engineering and other books that go into depth on how signatures work, partially because I hadn't figured out exactly how to do it in JavaScript yet. So, but what's a hash function? Well, a hash function takes a really long message and it boils it down to a unique thing that's a fixed length. So you get, like, you've got a 5,000 character long message. You're going to boil that down to something like a, I think it's either 32 or 64-bit hash. You can run the hash function on a really long message to produce this really short hash, and then you can sign that instead of signing the whole message. Remember how we said that when we're talking about asymmetric encryption, that's really slow? I would much rather sign a short little hash to verify that it came from Brent than I would like to sign and verify a 5,000 character message. We'll see an example of this in a second that's actually live. But, it's okay to sign that hash, and that speeds up the process. What hash function should I use? You should use the SHA-2 family. Do not, under any circumstances, use SHA-1. It has been broken all to pieces. You're asking for it if you use SHA-1. Don't do it. So, and you want to use, I would recommend at least 256-bit with SHA. What's a message authentication code, or a MAC? Well, a MAC allows you to test if data has been tampered with. Again, hash function takes big thing, makes it small thing. Message authentication code ensures that big thing is the same as the big thing that was sent. So this is tampering, this is shortening. Here's an example of authentication in action. So let's see here. We'll spin this up. Thanks to Yeoman, I can actually was able to spin up an ES6 app pretty quickly where I could use this. May have to come out of all right. All right, so here's an example of hashing and then macking. With SHA-256, you shorten a message into a unique hash that you can sign quickly with private key. So here, we've got quick brown fox jumps over the lazy dog a whole lot of times. This is a 1,204 length string. We can hash it to a 64 length string. We've got a copy of the message just to prove that the hash is going to be the same if we really have the same message. So there's the copy, hash of the copy, and then we get this copy message. This is actually being generated by live JavaScript. So I encourage you to go to GitHub. It's on my SOLTECH GitHub. It's called Fun with Forge. This is using the Forge library to actually generate an SHA 256 hash. And then down here, it's going to do an HMAC. So here we've got our original message. We've got our 256-bit key for HMAC and AES 256-bit encryption. Right, so there's our key. Key length is 32. That key length is going to be really important. And now I've got our HMAC. Yes, that is bytes. So this is, 8 times 32 is 256. That's why we can say it's a 256-bit key. Right? When we do this in bytes, you get a 32 length key. So we HMAC the message. We've got our HMAC length here, and then in bytes it's actually 32. So again, it's a 256-bit HMAC. Now, this is what we actually send over the wire. This is our message concatenated with the HMAC, and we format it to base 64 encoding to send it over the wire so that stuff doesn't get jumbled up. So you've got to convert it from like raw bytes into base 64 to actually send it over the wire. Do this, and we get this thing. This is our E. So Bob sends that to Alice. Alice receives the encrypted packet, decrypts it with the key and IV. We're assuming here that somehow they've managed to get the key and IV across the wire to each other. This is now the deciphered packet. So here's our HMAC, and here's our message. Now because we know the length of the HMAC, it goes to a fixed length, we can now essentially just split the string out, and we can pull the HMAC out by splitting the payload according to the HMAC's length. And then we got our plain text and our HMAC. We can now compute our own HMAC to verify the HMAC that was sent over. And if it's true, then we know that the message is authentic and it hasn't been tampered with. Okay? I should say here, we have not done anything with signing with private keys and then verifying with public keys. So we can't know for sure that this came from, I believe it's Alice that we set up here. Can't know for sure that it came from the recipient, but we at least know it hasn't been tampered with. Okay? So I encourage you to look toward that if you're trying to work through how do I do HMAC and SHA 256 in JavaScript. And I lost my PowerPoint. We're getting close. Tech problems. All right. So this is an example of Sigma protocol. For Sigma protocol, I'm going to skip this because we're short on time. I'll let you refer back to it. See Klutman and Vasily's video for an interactive example on how to do this. This offers a little more technical information because you're essentially going to compute your own HMAC of what's sent over, and you confirm that all of the cryptographic variables have not been changed. So as long as you do that, then you can know that I can decrypt this message and trust what's in it. Sigma protocol makes it really complicated because it's a protocol. Last thing is message numbering. We're not going to get into this, but you want to be sure that you number every message so that you prevent replay attacks and shuffling messages or just outright deleting messages by an attacker. So dude, tell me what to npm install already, right? This is all really heady stuff. Where's the fun stuff? I want to like run a CLI and just do it. So here's what you can use. NodeForge is a good project. It's got a ton of features and is the most granular by far, but it requires a lot of know-how to use. This is actually used for setting up TLS connections in JavaScript. So you can use it for that. You can't necessarily use it for Diffie-Hellman, right? But there are a lot of good tools in there. You can do RSA, you can do X509 certificates, you can do AES 256 with various block cipher modes, and it has by far the most documentation of any of these libraries. It's still confusing, but it has the most documentation of everything. OpenPGP.js is something you can use for basic things like email, but there's a lot of magic that runs under the hood. it actually uses Galois counter method as its block cipher mode. So remember how I said that that does both authentication and encryption? That can get a little confusing, but there are a number of block ciphers built into OpenPGP. If you drill down into their unit tests, you can see that they're there. It's a little difficult to figure out sometimes with OpenPGP.js exactly what's going on under the hood. But there are unit tests that you can pick through, and those are okay. Finally, there's libsignal protocol JavaScript. This is Signal's, it's Whisper Systems JavaScript library for the Signal protocol. This is probably the most feature-rich library of any of the ones up here. I say probably because there are like 5 lines of documentation. So let's take a look at this. If I go to, let's go to Whisper Systems. Go to the GitHub. Here is Whisper Systems documentation for libsignal. There's a few things there.